All right, I'm coming at you live from the Tokamak Hall. Behind me, we have Station 3, where we are getting the vacuum vessels all prepped to be put into the Tokamak. And something that is big and new is that we have the second half of the vacuum vessel behind me here. In order to confine a fusion plasma, one of the conditions that you need is to have it in a vacuum, kind of like outer space. So you need to have a chamber where you can suck all of the air out and create a condition where the only thing, literally the only thing inside of that chamber is the fusion plasma. And so that's why it's called a vacuum vessel, because it is a vessel in which you pull a vacuum and you evacuate all the air before you puff in that tiny amount of fusion fuel and then ionize it and turn it into a plasma. All right, so the vacuum vessel halves are currently apart on this stand, which we call Station 3, and there's a bunch of work that's going on to prepare them before we eventually bring them, both of the halves together and complete the tokamak. So the first thing that we're doing is measuring all the surfaces, but then after that, we're going to start doing things like installing the tiles that will be the plasma-facing surfaces on the inside of the vacuum vessel for things like the inner wall and the diverter of the plasma. We're also going to start installing some of the diagnostics and the instrumentation and controls even before everything is put together. So what are you doing right now?
So we are we're measuring the location of all of the ILM studs.
It's a lot of these studs.
So it took like 2.5 days to measure.
Oh my God.
East half. So I'm just grinding through.
Just grinding through.
Someone's got to do it.
This is really cool. Be able to actually say that you touched all the different pieces of it. Every single stud.
I know.
One of the few people. And then eventually there's going to be a star in this space, which is the craziest thing.
Yeah.
Pretty gnarly. One of the crazy things about these vacuum vessels is this is where we're going to be containing the 100 million degree plasma. So that plasma will be filling up this space. And you can see these studs next to me. We're going to be installing the tile carriers that have our tungsten tiles that will be the plasma facing surface. And those tiles will allow us to basically take the heat as the plasma cools down, but it's still pretty warm by the time it gets to the outside of the vessel. Most of the heat is actually going to be exhausted in things called the diverters at the top and the bottom of the vacuum vessel. The fusion plasma that we create is going to be contained inside of this vacuum vessel. And the hottest part is going to be at the core, which is going to be about right here, sort of in the center of the vacuum vessel. And then as you move outward from that core, the plasma is going to cool down. And so part of the reason that we need magnets is because you don't want the plasma to touch this material surface, because if it touches this material surface, it will cool down quite a lot. And we don't want that. We want the fusion plasma to be very, very hot. And so what the magnets do is they push the plasma in kind of away from these walls. And so you get a gradient where you have the very hot plasma in the center, and that temperature goes down as you get to the edges of the plasma. So the plasma is going to exhaust energy in a couple different ways. And the primary way is in something called a neutron. The other way that plasmas exhaust heat is through the alpha particles, so helium atoms that are generated in the DT fusion reaction. You can think of those as hot, charged helium atoms that still bounce around in the plasma and keep it hot. But once those helium atoms deposit their energy to the rest of the plasma and they cool off, you have to have a way to exhaust those and the remaining energy that's still in them. And that's what these diverters are for.
There are a lot of things about getting real hardware that you don't realize when you start the design. So now that we have the vacuum vessel here, we're realizing a lot of differences from what we maybe intended the design to be, or like what was possible with the weldment of the vacuum vessel. So we're changing a lot of the diagnostic designs to fit the puzzle pieces that were given with the vacuum vessel. So a lot of these studs that you see already are going to be for cable brackets. Some of them will be stud patterns for specific sensors to go down on, like bolometers and neutral gas sensors. Yeah, you see these two plates here. These are support plates. Yeah, these are steel support plates that are reverse engineered and then bolted to the vacuum vessel. The reverse engineering process actually makes it so that the tiles will land in like a very, very specific position with respect to all of the other tiles, with respect to the whole vacuum vessel, with respect to the plasma, so that we can very tightly control how the plasma is going to move and make sure that it doesn't damage the tiles during operation. In Station 3, which is this phase of the assembly, we have 384 support plates that are going on, and each of the support plates have about 4 carrier assemblies on there, and each carrier assembly has another 4 tiles on it, so it just is a huge number.
The reverse engineering tolerance is about 200 microns, depending on the location where you are. Each of the tiles basically shadow every following tile behind it. The heat flux that these tiles basically experience is incredibly high. And so if the tile isn't placed perfectly in the right spot, you get a really hot spot that will literally melt the tile away. And so the precision of where these are located is super important so that the plasma doesn't erode the surface.
Yeah, so there's a few different types of big holes inside of the vessel. We have the mid-plane ports, which are along the mid-plane of the vacuum vessel, as you can see here, and we have the off mid-plane ports, the upper ones here and the lower ones down here. The lower ones are covered so that we don't fall through during assembly processes, but we'll soon uncover them since we'll have to route cables out the ports. As you can see here, we've done a trial install of one of the sensor sets.
My name is Elliot. I am a part of the tooling team under the SPARC assembly team. We work on all of the big orange stands that you see around you. My job particularly focuses on large support structures and lifting equipment. We get asked quite often if these orange stands are permanent or temporary, and the answer is anything painted orange is temporary. These are carbon steel and must be removed before the vise is turned on. We cannot even bolt things into the floor due to the amount of rebar that we need to support the weight of the vessel. It's interesting. I think as a tooling team, our job is to kind of remain unseen, right? You look at something like the vacuum vessel lift, which is hundreds of hours of engineering work for 30 minutes of uptime. The goal is that that appears smooth and easy. This was a really cool moment because when we landed this, we were able to look at something that we had been designing in a CAD model for months and months and months. And you land the second vacuum vessel assembly and you're like, that looks just like the CAD model, and that's great. That is months of planning, and to then see these orange stands here finally getting used with the SPARC components on them is a great feeling. These stands are temporary, but they are critical to the assembly of SPARC.
It feels cool to be, where the science is going to be and happening, and you're there and in it. You get to see everything that the plasma will see, right? I think that's probably one of the coolest elements of my job. SPARC's a really big project. We interact with a whole bunch of different people along multiple design teams. Sanaya and I, we do the same thing. We're co-patriots. We work on the same parts of the station. She's great at forward planning, getting day-to-day, solving through problems. Elliot's been a great support as a tooling engineer. He did all of the VV lift. He worked on all the tooling for it. It's great to be able to rely on them to do different things throughout the day as we solve issues and problems that we encounter.
So you'll notice that this vacuum vessel, the cross section of it, the shape, isn't a circle. It's more sort of like D-shape. The first tokamaks used to actually have circular vacuum vessels. Over time, we learned that it was actually advantageous to squish the plasma into more of sort of a triangular D-shape. One of the nice things about this process, even though it looks very complicated and there's a whole bunch of things going on, is that this actually isn't our first rodeo. So there's been 150 tokamaks that have been built around the world, and we're actually able to stand on the shoulders of a lot of the experience that has been gained from building those devices. So we're going through this complicated dance and we're really optimizing it as best as we can so that we can put the machine together as fast as possible. Because ultimately, the goal of SPARC is to get to Q greater than 1 as fast as we can so that we can then move to the next step of building ARC, which is the fusion power plant.